host for this session. First of all, I would like to welcome all of you again to the Big Tech Day 2026 here at the Motor World in Munich. This counts for both our local audience here in the Kohle Bunker 2 as well as for our remote participants in Zoom. As always, right after this talk, there will be a short Q&A session where you can ask all your questions. And for remote participants, feel free to ask all your questions in the Zoom chat, and we will just read them out for you afterwards. All right, so how many of you ever wanted to experiment with robotics but simply did not have a robot to experiment with? I mean, robots are expensive, right? And they are nothing anyone would simply have at home. What if I told you that you can actually build your own robotic arm for 120 euros yourself and just get started teaching it some cool skills? Today, you can learn how this is possible from Steven Palma, a tech lead at the LeRobot project from Hugging Face in Paris. Steven Palma, born and raised in Costa Rica, came to Italy in 2019 for his European Masters in Robotics Engineering. This was where I had the pleasure to meet him. Together we hacked into some robotic lawnmowers and built our own navigation software for it. 1 year later, Steven moved to France to finish his double degree and work with multiple robotics companies. Just in the beginning of 2025, Steven finally joined Hugging Face as a tech lead for the LeRobot project, where he now leads their mission to democratize physical AI. Ladies and gentlemen, please welcome Steven Palma.
Hey. Hello. 1, 2, 3. Can you guys hear me? Yeah? Cool. Very happy to be here, guys. Thanks, Philip, for the introduction, and thanks for the invitation as well. I'm Steven. I'm the tech lead. I do robotics at Hugging Face in general, so maybe raise your hand if you know already Hugging Face and have used it before. Okay, awesome. Very, very cool. And then keep it up maybe if you have used LeRobot. Awesome. That makes me very happy. Actually, the previous talk was touching similar concepts. They had some cool robots that we're actually going to see later down. So yeah, we're just going to touch up on the same concepts, but maybe with a different flavor. So let's start with Hugging Face. Let me see, if you are an AR builder, an engineer, a scientist, Hugging Face Hub is the platform made for you because it simplifies your work. It facilitates your AI workflows every day, right? And it does that by giving you all the infrastructure that you need to deal with the different things that we work with when we are working with AI, right? Datasets, models, and applications. So the Hugging Face Hub is essentially a platform where machine learning community collaborates on all these three different things. And that's kind of what the Hugging Face Hub is providing you, right? I like to see datasets as kind of like the ingredients, right? For, it's the source information. Then you have the model, which is kind of like the cooking recipe. And then you have the spaces, which actually are just applications built on top of the model, which will be kind of like the restaurant experience, right? So Hugging Face walks you through all the tools that you need in order to host, distribute, collaborate, version, edit, create, any of these three things. So if you are into the AI space as an engineer, maybe you just want to explore it, or maybe you want to architect your solutions around, make sure to give Hugging Face Hub a try, right? We are big in open source, as you might know as well. So then that means you can go find any of these three things in the hub just ready to use. Such that you can leverage immediately some models that have been published or some data sets that have been shared in the past in your own workflows or in your own architecture. Cool. But today I'm going to talk specifically about a project called LeRobot. And essentially, Hugging Face, when we noticed all this AI revolution, right, we thought about how can we, eventually this will get physical. And we wanted to put it available for everyone, right? So the question was, how can we make this? How can we leverage all the innovations from the LLM space into the robot behavior? And this is how LeRobot as a project was born. LeRobot is a project that makes AI for robotics more accessible with end-to-end learning. End-to-end learning, sometimes also referred as robotics learning, but it's essentially the technology that tries to put, let's say, an LLM, a VLM into driving the robotics behavior, right? So yeah, LeRobot is about that. It follows a similar principle from Transformers library. So essentially what Transformers library did for natural language processing back in the days where the field was very fragmented, right? Because everyone was doing their own thing. Everyone was reinventing the wheel in their data pipelines, and in their policy architecture, and their model architecture. Well, we unify all that with a single library, and that allows us to level up the field, right? So we're bringing the same philosophy, but for robots, for physical AI. How are we accomplishing that? Well, essentially, I like to see LeRobot as it follows mainly these 3 principles, right? The first one is state of the art. So we have all seen or watched in social media robots doing crazy stuff, right? Crazy tasks that were historically very hard to accomplish, like backflip, maybe cooking something, maybe interacting in a way that we have never seen it before. Because in the past, all this was always described in a very analytical manner, right? Very deterministic. And that was very hard. It always required you 4 PhDs and months of effort to accomplish what we think it is a simple task to the robot doing it in a consistent manner, right? So with the state-of-the-art principle, what I'm trying to explain is that the project is based on the latest progress on the field, on the end-to-end robotics learning field, right? So that is, again, bringing all the innovations from the LLM space into the robot and all the tools that surround that. So that's the first principle. The second principle is, OK, cool, we can do that. But if it continues to be very hard to use, then no one is going to experiment with that. So accessibility is a very important part of the project. And we accomplish that by, and we're going to see it later, well, first, the project is fully open source. So, OK, cool, everyone can access it. The second thing is that it is very easy to use, such that you feel encouraged to just give it a try. And then the third part is that you don't need top-notch hardware in order to start moving something. So that's the second principle. And then the third one is community-driven. And this is, again, going back to the same principle, not to the same principle, to the same philosophy that Transformers had, which is, hey, let's unify the field such that we can all leverage on each other's discovery, right? Cool. So, great. But what is LeRobot, the project, actually about? And this is maybe a workflow that was somewhat described in the previous talk, which, well, when they were referring to imitation learning. But essentially, LeRobot is a software library that allows you to experiment with all the steps in the end-to-end learning pipeline that you will require in order to make the robot do a task, automate a task in an autonomous way, right? So then that means they're usually divided into these 6 steps. The first one is the robot itself, the hardware. So with an LLM, you only need it on a computer and then natural language to interface with that. Well, but if you want to put that into the physical world, if you want to like automate a proper task, then you're going to need something that moves, right? And that's where the robot comes, right? The hardware itself. So in LeRobot, we put available some hardware out there such that people can easily access it and then have something moving right away. The second thing, it is teach and teleoperate. And this is because how this technology works, or at least I'm talking still here about imitation learning, is that you go, you do it yourself, you show the robot how it is done, and hence later on the robot learns how to do it, right? But then that means that you need a step in between, which works kind of like the glue between the hardware and the software, such that you can move the robot programmatically, right? And then that means using different teleoperator devices, and then using different robots in general, right? Then the third part, which is the dataset. So, well, turns out, OK, we have the hardware platform, and then we can move it. Then that means that we can start teaching the movements or teaching the tasks that we want to accomplish. But then that means that we also need to start recording the data that we're doing, right? So that's the third part, the data collection, which we're going to touch more into details later on. Once you have your data, which is now going back to the first slide, in which I say dataset models and applications, you have, okay, you already have the ingredients, which is essentially the recorded data of your task. Now it's time to cook your model, right? And that's essentially what is going to be the brain of the robot, right? The intelligence, which is where most of the innovations are happening nowadays. After that, there's 2 different steps, which is, OK, once you have your model, then you want to put it into the robot, see if it actually automates the task, right? See how it goes in the real world, which is the 5th step. And then the 6th step is, well, cool. I tested already in my physical robot, but I also want to see how it will perform in different scenarios, right? Or maybe I want to see if my new model is better than the one before. And that is the benchmarking part, right? So we're gonna go into detail in each of these steps. But essentially, LeRobot as a project, right, is a software library that allows you to go through all these different steps, so you can actually experiment with all of them and build an intuition, build context, understand the principles that allow the robot to do crazy tasks, right? Well, we're gonna see some of them later on. OK, cool. So let's go to the first part, the robots. If I go and I need a robot that it costs $100,000, then I'm not going to experiment. I'm not going to use it, right? It's too expensive, especially if it breaks often, right? I'm not going to have it there in the garage lying such that I can easily play with it in the weekends. So what we did at Hugging Face was to design very low-cost hardware that is accessible to anyone. And accessibility has different flavors, right? In this case, of course, it is the price tag. As Philip mentioned at the beginning, each robotic arm on your left costs $100, $120, depending on where you are. But it's also very easy to use. It is also open source. And most importantly, if it goes and it breaks, then you can go and replace it, right? Because it's not that expensive. Maybe you can just 3D print another part, or maybe you can hack it, right? So this is the part in which we lower the barrier of entry from the device itself, right? These serve as a vehicle for people to start with something, to have something there in their garage, to have something there in their research labs that is able to move, is able to do a task, right? Cool. So this is the SO100, very popular nowadays. I think if I had to estimate it, more than 15,000 robots like this have been at least created and sold. Of course, it is hard to keep track because people can build it at their home, right? They can just 3D print it and so on. But some of the numbers where we have got, there are around 15,000 robots. And then on the left, we have the Kiwi, which is an SO100 mounted into wheels. It's a very natural step forward, which is mostly to play around with navigation and so on. Cool. OK, awesome. So as I said before, you also need to make sure that the hardware that is available is easy to be used, right? That you can move it in a programmatic way. And this is where the control and teleoperation part of the project comes into play, which essentially allows you to, from the moment that you plug your robot or your new hardware to the moment that the robot is actually moving, it just takes you 10 minutes, right? You don't need to figure it out the entire thing, because all these tools are already available in the library. They're easy to use. So then you don't have to deal with all the complexity behind how I'm going to move this, right? We offer the right API with the right levels of abstractions and some of the hardware drivers that we at least support natively out of the box. But the important part in here is that the project is very much extensible. So let's say, as they say in the previous talk, let's say that, of course, I have a couple arms that I can use as a leader device. But maybe tomorrow I want to use a VR headset, or maybe tomorrow I want to use a different embodiment and so on. Well, it is easy for you to register such device into the project itself, right? But this is essentially all about, cool, we have the robot, now we can move it. All right, then we come to the datasets segment of the project, which turns out to be very important. And it is due to the things that I mentioned at the beginning. Given that the field, the robotics learning field, is very new, and by new I mean maybe 5 years, but not by 5 years, maybe it got trendy the last 3 years, but that's already a long time ago in the AI space. Everyone was just doing their own thing, right? So we had this problem in which a research lab will go and they publish their new research, maybe a very interesting model, maybe they recorded a specific task in the lab. But when someone else was trying to replicate that, well, it was very challenging because I don't have the same infrastructure as they had, right? And maybe, sure, that data set that they collected was very useful, but how can I translate it into my own format so it kind of plugs into my training architecture, right? My training infrastructure. So what LeRobot did as a project is that it is homogenizing the dataset format that we use for physical AI, right? So nowadays, if you go and you use the project and you want to train your model, and maybe you want to record your data, we can all be speaking the same language from a dataset perspective. And this is very important because, at least for the LLMs, well, we already had an internet worth of data available for us, right? But for robots, for specific tasks, well, we don't have as much data as we had. We don't have Shakespeare's book, right, for I don't know, cleaning a dishwasher or this type of things. So sharing data sets across the community becomes very important, and it has been a very big bottleneck, right, for pushing the field forward. So what I'm trying to explain here is that at least from the LeRobot perspective, the project itself, now we're all speaking the same language. We all now share and distribute a common dataset format. And we leverage the Hugging Face Hub infrastructure in order to do that. Right? And I record a robot. Actually, I think I have it in the next slide. I go and I record a task happening in the supermarket of my robot, whatever that embodiment is. And then I can easily go push it into the Hugging Face Hub such that everyone can leverage, right? I can easily distribute it to everyone. And now if you're, for example, training a model that will try to automate a task related to the same supermarket or maybe with the same semantics of the task, then you can go and use that data set in your training pipeline, right? Fortunately, it has been very popular, right? The project is less than 2 years old, and we already have 100 terabytes worth of physical AI data in the LeRobot format, fully open source, in the Hugging Face Hub, right? So chances are that if you want to do a task, which is to a certain extent common, someone else already recorded the data, right, that you can use to train your robotics model. Not only that, in LeRobot, it is not only about, OK, we provide the standard for the dataset, the physical AI dataset, but we also give you all the tools that you need to experiment with it, right? You can visualize the dataset, you can edit, you can add, remove episodes, you can merge different datasets, and so on, right? So it's more about the complete experience on how do you manage, process your data, and making sure that that happens in a common framework such that everyone can later use it as well. Cool. Then we have the models, right? And this is arguably the most important part of the project, because this is what it is bringing the intelligence to the behaviors, right? We have all seen the videos of robots doing crazy stuff and so on, and that is because we're now using the architectures, the similar concepts that were used for the LLM breakthrough into the robot behavior, right? This is what the field is about. Putting, instead of describing in a very analytical and deterministic manner the behavior of the robot, we go and we put a model instead, right? And maybe a good analogy is to think about If you go and you want to catch a ball mid-air, you don't need to understand, you don't need to derive the gravity, the motion laws in your head before doing such motion, right? You get what you see, which is the ball coming at you, and then that image, that sensory input, gets fed into your own internal model, right? And the output is, hey, I need to jump, right? I need to jump if I want to catch a ball, right? So this is thanks to the new architecture of these models, right, of robotics learning. In this case, I'm showing ACT, which is one of the kind of like pioneers, right? It's very basic. But in LeRobot, we also support things a little bit more complex, which were touched in the previous presentation, but still, this is a VLA, which stands for Vision Language Action Model. This is specifically the architecture from GRUT 1.5. And this is just many of other architectures that you can experiment with. And the idea in here being that LeRobot as a project, you can go and you can pick the model based on your application. Maybe not even only based on your application, but also based on what you want to experiment. Maybe on the data set that you have available. Maybe on the compute that you have available, or maybe even the hardware, right? So I like to see LeRobot as this one-stop shop for robotics learning. You go and you pick up whatever you need out of it. Not only that, we also have things like some other models that are not precisely related to the movement or the behavior of the embodiment, but they nonetheless help you with all the pipeline that I described at the beginning. In this case, we're seeing a reward model, right? And what this is doing is that, sure, you have your data set. Let's say that you went and you record, in this case, the robot putting the biscuit inside the microwave. And it is easy if you have 10 of these episodes, right? And then you go and you check your data, and you say, like, OK, yeah, this is exactly what I want my robot to do. But if you have 100,000 episodes, then it is not as straightforward to go and check whether all the demonstrations are doing the thing that you actually want it to do, right? So reward models, in this case, this is just an example of one of them. They allow you to get an insight of whether the task that you were trying to accomplish in the demonstration is actually accomplished, right? And they give you a score based on like the progress of the data set, right? And this is also a model that you can train in LeRobot, which is, again, this is not going to go and move the robot, but it will allow you to, in this case, decide which data sets are more important when you're training the other models, right? Because I can easily go and discard the data sets that maybe went above a threshold, right? Or maybe I still want to use those data sets, but I want to having them represented at a lower degree in my training run, such that, hey, whenever I'm training my model, make sure to weight better the data sets that actually accomplish the task and do not put a lot of attention into the ones that don't. And as we're going to see later, actually, the data set quality turns out to be very, very important for the model itself, for the model performance. And this is just due to the fact that imitation learning, it is as good as their demonstrations, right? This is the paradigm of behavioral cloning. The robot will never do it better than the demonstrations that it had, right? So this is why data quality is very important. And with all this, what I'm trying to say is that in LeRobot, you don't only have the models related to the robot behavior, but you also have the models related to any other thing that might help you in this end-to-end pipeline. Some other examples is we also support reinforcement learning, right? Such that you can play with it. So far, I have been focusing mostly in imitation learning, but we also have a reinforcement learning pipeline that you can use for training your robots. Cool. And then we have the inference step, which is the fifth step. And this is just, OK, I have my model already, and I need to see how it performs, right? And for that, there are plenty of strategies. Right? There are a lot of things that are happening. In this case, we have a simple use case in here in which the robot was trained based on demonstrations to pass the cube from one arm to the other one. And then you go and you do the physical rollout to see if it works. But then there are plenty of strategies in how do you run the inference, right? For example, it can be asynchronous. It can be synchronous. It can be on the edge. It can be on the server, right? Maybe you don't have the compute next to the robot. Maybe you need to compute it somewhere else. You need to deal with latency, right? There are things like RTC that are also into the field nowadays, which is essentially because the workflow, how this looks like when you're actually running the model is that you pass the inputs, you do the forward pass, and this gives you the next 30 steps, right? Computing those 30 steps took some time, right? So then while you execute the 30 steps and then you finish your chunk, you get the new sensory input, and then you do the forward pass. So then it is very synchronous, right? And that means that the robot might do an action, and then it stops, collects the new information, gets the new chunk, and then continues, right? And of course, although that might work for little scenarios, like the one on the right, it might not work for a little bit more complex on the left, right? In which you need that iteration loop to happen faster, right? So this is everything related to the inference step. Not only that, while you do your physical rollouts, once you train your model, you run it into the robot, it's not like you don't want to continue recording your data anymore, right? Maybe even the data that is being produced out of the physical rollouts is as important as the demonstrations, because you wanna get the data in order to further train your model, right? Maybe in some failure scenarios. Maybe you want to record everything that is happening, or maybe you just want to record a small section where the error happened, or maybe you want to interrupt the robot halfway so you can teleoperate and teach it how it should actually behave, right? What happens often, the first time that you run the model, is that, well, first, your robot most likely breaks. The second thing is that it might try to do the task, and then you see it that it is somehow achieving such, but then it just does something else. And in that part, you can, for example, interrupt the policy run, take over with the teleoperator device that you have, and then complete the task, right? And while you do that, well, that's important data, that's valuable data that you want also to use later down to further train your model. Okay, so what I'm trying to say is that all the inference part is also taken care of in LeRobot. Awesome. And then lastly, we have the benchmark, which is, as I said at the beginning, well, you need to have a grasp of how good your model is performing. And the challenge in here is that as the models get more general and general, then there are more scenarios, there are more tasks that they can do, and you can easily run out of ideas, run out of physical space in your little workshop, right? So this is why this is an academic. Well, we actually support mostly academic benchmarks in LeRobot. This is the one called Libero, and how this happens, or how this works, is that sure, you pass your model, and then a lot of simulations get run in the background, and then at the end of the day, you get a success rate of like, hey, this model performed or had a success rate of 80% for these type of tasks, right? And the type of task might be generalizing between objects of different color, or maybe generalizing on different instructions, right? Maybe it's the same scene, but the instruction of, hey, pick up the banana or pick up the strawberry was different, and then he was always picking the banana, right? But, well, at least he grasped something, so OK, cool. So these academic benchmarks helps you just figuring out how to further iterate with your model. OK. And then I go back to the third principle that I mentioned at the beginning. What is it that LeRobot has become so popular as a project? And that is because we put the community as a first-class citizen, so to say. This is a video of a global hackathon that happened last year. Over 2,000 developers. We're in the same weekend. We came together, and we were just doing fun applications with robotics learning. We were collecting data, we were training models, we were seeing what was going on after, and then we were sharing such data sets, we were putting those models available in the hub such that everyone can try it, right? That's the magic of it. This is a map, by the way, of all the cities that participated in such event. And the crucial part in here being that it is very important to build in the open. Why? Because if I go and I record the data set, someone else can use that data set to train their model, and that maybe enables a breakthrough in that part, right? And that breakthrough, if it is shared, then it might enable another breakthrough in the benchmark space, so to say. And this is where open source comes important in physical AI space, because we can all decide collectively how we're going to shape this technology, right? And we can share between each other all the learnings from our experiments. OK, so well, turns out, or so far, I have been focusing a lot in the accessibility part of the project, right? And all the examples that I have showed you, more or less, are using a low-cost robot, the SO100. But what happens if you have something a little bit more capable, right? This is, we got a slightly more capable robot. We got slightly more compute. And we went and we recorded slightly more dataset hours. And then we used the same project. We used the same concepts, the same principles. And now suddenly, a robot can go and fold T-shirts autonomously. This is historically very hard to achieve from a deterministic point of view in robotics, right? But the crucial part in here being that it doesn't matter if you don't have the most capable hardware. It doesn't matter if you don't have the capabilities to go and record 100,000 hours of physical AI data. It doesn't matter if you don't have the latest GPU in a big cluster, right? If you go and you start with small applications, with the SO100, just simple pick-and-play tasks, the same principles, the same context that you build while experimenting with such can be applied later down if you can scale in any of these 3 dimensions, right? Even you get a better hardware, you get more compute, or you get more data sets. Just to give you an idea, actually I can go to the next one. All this experiment that we did is fully open source, right? We disclose everything. The model that we use, the data set that we use, all the process, and all the learnings, right? Such that people can go and replicate it. Not only that, they can learn our mistakes, right? They can empathize with the things that are missing in the field, right? And this goes back again on why it is important to build in the open. Just to give you an idea, maybe for now I'm going to go back to the previous slide. To just give you an idea, we had to collect around 150 hours worth of data in order to make this happen. And that turns out to be actually very expensive from a logistics point of view, right? You need multiple setups. You need teleoperators that are doing the task over and over again, right? You need all the infrastructure in order to support you on that. Then you have all the compute, right? And all those different, you have all the experimentation that happens in between. It is not that you go and you train your first model, and your first model, boom, just works right out of the box, right? There's nonetheless some engineering to be done. I like it because, sure, robotics has become easier for certain tasks, but that doesn't mean that it's solved, right? I mean, there's a lot of engineering challenges still. It is just that it has always been a composition of systems, one of which has become better than before. But that doesn't mean that everything is solved. So what we did is that we went ahead and we published our results such that people can leverage on that as well. OK? And then, well, LeRobot as a project, it also turns out to be very much extensible, right? So let's say that you want to bring your own hardware. Maybe you want to develop, you want to experiment with your own policy architecture. Maybe you want to bring your own benchmark or so on. Well, the project is made for that. right? You can just go, plug your own things, experiment, and give it a try. OK, so now, sure, I have been focusing a lot on the hypothesis part and the making part, but well, the progress of the project and the progress of the technology has been so strong that we have multiple players already involved, right? And of course, I'm not going to list everyone in here, but the important part is that we have academia, we have research labs, we have startups, we have big enterprise, and then we have people that just might want to give it a try on the weekend. And we all come together trying to solve the challenge in a common framework. And this is, again, the importance of building in the open. OK, so maybe after all this, you say, like, OK, but maybe it's still too complicated to try, right? But it is not like that. This is mostly for developers. It is just a Python library. So you just go, pip install LeRobot, and then from the moment that you do that to the moment that your robot is moving, it takes you 10 minutes, right? This is yeah, great. This is the accessibility part of the project, right? If it is too hard, no one's going to try it, right? Just historically, when we have people that maybe started with robotics, and then they further in their career drifted away because, well, it's just too complicated. Oh, now we're seeing a lot of people who wants to go back into the field and give it a new try with fresh eyes because we can now do things that were not, OK, maybe they were possible before, but they were just too hard. Now they're a little bit simple, right? And we have, fortunately, enough investment, enough attention into the field to do breakthroughs in all the different steps that I just explained, right? We have players that are focusing on making very good hardware that was not available in the past. Maybe going and collect a bunch of datasets just so everyone have it available out there. Maybe there are other players that are focusing on only the model architecture and so on. OK, so we tend to publish frequently some updates about the project, just to give you an idea of what's going on. The field is moving very fast, right? So we also need to get a grasp of what are the important, what are the things that are worth adding into the project or not, such that people can continue experimenting with that. To go back to the T-shirt folding video, what type of modalities do you think we needed in order to accomplish that? Well, essentially, we only used 2 sensors, right? We used 3 cameras, 3 RGB cameras, and then the encoders from the motors, just to get the robot state. And that was pretty much it, right? That's all what we needed. We didn't need haptics, feedback. We didn't need torque, measurements. We didn't need depth. We didn't need to control the lights in the workstation, right? And it is just part. This is only showing us how capable the technology is becoming today, right? And hence, there are a lot of innovations happening every day. OK, so the previous presentation that I also showed biped humanoid, this is actually very new. This was released less than 24 hours ago. But this is just to show you that we continue to lower even more the barrier of entry from the hardware perspective. I have been focusing mostly about what happens in the library, right? What are the different steps of robotics learning and so on with the cheap platforms like the SO100, which was released some time ago. But we in the team, we also continue to do some more experiments about, hey, how can we bring even more open hardware available for everyone to experiment with? In this case, this is a biped. This is around $2,500, fully open source. The USDs, the electrical diagrams, the runtime, the training recipe that we use in order to achieve these little motions, which I'm not gonna. We don't have a video yet of the robot running and doing some crazy tasks. But the idea is not to go and build the most modern humanoid out there. It is mostly about making sure that everyone can just go and build something similar build an intuition, build the context, understand the principles of the technology that is making this happening. And then lastly, I'm going to leave you here with some links. Don't get me wrong. This is actually the most important slide of the presentation, right? Because LeRobot is very popular thanks to the community, right? It's because people feel encouraged to give it a try. It's because people feel engaged with sharing their learnings, right? They want to go explore in the hub. They want to go and explore in the hardware space, all the different things that are happening. So we have a Discord server. We have a Twitter account in which we publish all these different funny videos, including the ones that didn't make it to the final video, polished video, and then the GitHub account. Make sure to get involved. Ideally, after this talk, you go and you get your hands into an SO100, and then you just go and you teleoperate it. And then you're going to realize very soon that the first moment that a robot is moving autonomously with a model is actually very exciting. It never stops surprises me when the robot, for some reason, it just heads towards the cube, picks it up, and it moves it into the bucket. And it feels almost magical. You never know how is it that the model was able to do that, right? Well, of course, you have an idea of the policy architecture and so on, but like, it is only until you go and you give it a try that you really feel the excitement about all the innovations happening in this space. So I'm Steven. I'm the project lead of LeRobot. So if you like what you see, then come talk to me later on. Thanks a lot.
Steven, thank you so much. I'm pretty sure you inspired many people here to try out LeRobot themselves and get their hands dirty. So now we have almost 10 minutes for a couple of questions. So let's start here in the audience. There's a question back there.
If you don't mind, I have two different questions. First one is about the open data that you mentioned. You said you had 100 terabyte of data collected. Can you frame this a bit more? 100 terabyte of text is a lot. Of time series, it's respectable. Of video, I really have no idea. Do you have, can you frame a bit more what kind of data that is?
Yeah, sure. This is mostly video data, right? Because the video is the one that is taking most part of the storage over there. Of course, we also have the state of the robot, kind of like the encoder measurements, but that fails in comparison, and just in terms of size, with the videos and the images collected. So it is mostly about the modalities that the current policy architectures are able to leverage. There are no, for example, point clouds, right? Because so far, at least within the robotics learning perspective, there's not a big model that is leveraging in an important manner the point cloud data. So then people don't feel encouraged to go and share that one to train their model, right? Because there's no model that they can use easily to leverage that data. So most of these 100 terabytes worth of data is either images or video, plus the state of the robot. And it is, of course, contributed by different players on the field, right? There is, I think I got the graphs the other day, although the SO100 is kind of like the most popular robotic framework out there that people are using the project with. It only accounts for maybe 15% of this 100 terabytes worth of data. So then that means that all the rest is just different embodiments, which might be contributed in a large scale by certain companies that are maybe only doing data collection experiments, but then they decide to go and put that data available for everyone. So yeah, modalities are mostly vision and then the robot state.
Thank you. And the second question, you said that this is, or the or the training architecture is somehow about imitation learning. So does this mean that simulation does not play a significant role in training these models?
Yeah, it absolutely does. It does at 2 levels, which, yeah, that's true. I didn't add or I didn't mention anything about simulation in the LeRobot project, but we also have some tools related to simulation. Simulation comes important in 2 different moments. The first one is when you go and you collect data, right? Maybe you don't have your physical rollouts to go or your physical space to go and like collect everything. You want to do that in a simulated manner. The second part in which the simulation comes important is when you want to evaluate the model, right? Similar to what we saw in the academic benchmarks over here. This one is, of course, a simulation, right? But there are different options out there, right? NVIDIA, for example, has been doing an incredible job at just bringing some simulation tools into the space. How I like to see it is that you can use simulation for data collection, sure, but that also is going to complicate your pipeline because you need to merge that data with your physical data, and also to perform the movement in the simulation, you still need to teleoperate the robot to a certain degree to like make it accomplish the task. You can also use reinforcement learning for that, but it complicates that part of the project. I believe simulation, at least nowadays, comes more important in the evaluation side of your model.
So maybe to be more specific, does simulation play any role in that T-shirt folding?
No. Yeah, that's an amazing question. We didn't use any simulation aside from running some standard benchmarks just to get an idea of if the model was actually learning something. But we didn't use any simulated data in the T-shirt folding experiment. And then it gives an idea, it gets a further idea, which is, hey, if we were able to accomplish that task with 150 hours worth of data, physical rollouts, then imagine what a robot could do as soon as we can unblock all the potential of simulation for data collection.
Yes, so thank you very much for the very interesting talk. I would have the question, how strongly tied is the collected data to the actual physical robot? So for example, if you now publish a bipedal robot, and you previously said that collecting the training data for the T-shirt folding example was a significant investment, are there approaches to reuse that training data for, in particular, for example, the bipedal robot?
Yeah, so it all comes down to your policy and model architecture, right? If you are using a model that, in theory, can be cross-embodiment, then you can precisely use all the data that you have available, right? There is still going to be a fine-tuning step in which you take the base model and then you tell it, hey, these are the degrees of freedom that now you can play with, right? And that might be an arm, that might be a leg. Go and figure it out, right? I'm not saying that that's easy to accomplish, but it is possible, right? Also because as we said, collecting data is very expensive. So the more that we can reuse it, the best, right?
Okay, last question.
Goes in a similar direction. So when you say the state of the robot is part of the shared datasets, so what is it? Only basically robot-specific state, like the joints and how many joints it has, or something more universal, like, I don't know, like Cartesian space coordinates or something like that? How do you approach it? Like universal things and like chassis-specific things?
Yeah, this depends on in which action space you want to work on. One direction, just going back to the simple example, let's think about the T-shirt folding experiment, is to, sure, record the robot state in terms of like the encoders, right? What is the position of every joint? but you could also train a model that learns from the n effector space, right? And then that will be your robot state. Does it make sense? So then that means that, sure, most of the times, if you keep it closely together or close one-to-one to your embodiment, then probably you're reducing the amount of steps that something can go wrong. But if you want to work on the n effector space, that's totally possible. It is just that you're going to have a layer in between, right, in which you are nonetheless reading the encoders of the robot, but then you're also applying the inverse kinematics that you need in order to get the n effector space. Another interesting question will be, for example, what can we do with egocentric data, right? Things like, hey, I put a tracker on my elbows, and then I go and I do the task. That is still pretty much on research level, right? And it hasn't landed just yet into the project. Yeah.
All right, Steven, thank you so much. I guess there will be many more questions, but Steven will be around here at the event, so feel free to catch him anytime. All right, Steven, thank you so much.
Thanks.